Hey everyone, and thanks for tuning in again. Today's video will be about checking regression assumptions. So I'll be showing some approaches I use for checking assumptions, and remember, out of the Gauss-Markov +1 assumptions, only 3 can be tested with sample data, and these include homoscedasticity, independence of errors, and normality of errors. The approach I'll be showing is a quick and informal screening. So this is what I call my first line of defense. So in every dataset, most assumptions are typically already violated to some degree. So the goal is really to see if it's bad enough to warrant further actions. So the main question is, does the evidence suggest that I need to worry about the results of my analysis being affected? So remember, when some of these assumptions are violated, it could bias our estimates, and it could also change, it could upwardly bias or downwardly bias our standard errors, therefore affecting statistical tests. And we don't want that to happen. So if the evidence does show that I need to worry about the results of my analysis being affected, I can follow up with more formal tests, which will be covered in other videos, the diagnostic videos. But if not, then I could just proceed with my analysis as usual. So there are many approaches and sets of approaches for assumption checking, and this is just what works for me. So ultimately, you can take and run with what works for you, and you can drop what doesn't. Assumption checking, whether formal or informal, are simply rules of thumb, which are usually not generalizable to all situations. So none of the rules that I talk about here are set in stone, and they change on a case-by-case basis. Sometimes, not all the experts even agree on what the rules of thumb should be. So the purpose of assumption checking is to build a compelling case that either shows that assumption violations will not affect the outcome of analysis or are not likely to affect the outcome of analysis, or that assumption violations have been addressed to an extent that the outcome of the analysis will no longer be affected. So again, the approach I show here is how I begin to gather evidence to build my case and many times I'm talking about reviewers, my case for reviewers. So there may be a bit of overlap in this video with the regression diagnostics videos, but again, this is just a quick check, mostly based on visual inspection of graphs and plots. More formal statistical approaches for detecting assumption violations will be covered in the videos on regression diagnostics. So with that, let's go ahead and get started. All right, so I have R open now, and hopefully these templates are starting to look familiar. So again, I just have these little headers that I've created to organize the syntax that we're going to write using hashtags or comments. All right, so there's a new data set that has been uploaded online. The data file is called regdata3.dat. And so that is what I'm going to start with, is reading in our regdata3 dataset. So again, I'm just going to use the read.table function. I'm going to provide as my first argument the location of the file. Second, I'm going to indicate that there is a header. So the first line of my dataset, those are variable names. And then I will designate the separator as tabs. So this is a tab delimited file where every observation is separated by a tab. I'll go ahead and run this line, and we can go ahead and take a look at our data set, make sure it read in correctly. All right, so 150 observations, which is what it should be. And then I have 2 predictor variables, x1 and x2, and then I have y1, y2, and y3. So the x's are predictors, and the y's are different criterion variables that we are interested in. So what I'm going to start with here, with checking assumptions, is I'll just go ahead and print out some descriptive statistics. So I'll load the psych package, and then use the describe function for our regdata3 dataset to get some descriptives. So here we have our descriptives, so we have means and standard deviations of each of our variables. We have the min and max here. This is really useful for seeing if any values are out of range. Everything here looks pretty good. And when I say it looks pretty good, it's because I generated the data, so I kind of know where the values should be at their lowest and where they should be at their greatest. So if you're working with a data set that you have familiarity with, the minimum and maximum could be helpful for showing you if anything is out of range. And then I also have skew and kurtosis, which I'm particularly interested in so that I can look for any... remember that the assumption is not about any particular variable, it's about the residuals. So we want to make sure that our residuals look normal. And a good indication or proxy of that is looking at the distribution of our criterion or our outcome variables. There are no distributional assumptions on the predictor variables, so we're not worried about x1 and x2, but we do want to take a look at y1 through y3 to make sure and see if those are pretty close to normal. So when looking at skew and kurtosis, a rule of thumb is plus or minus 3. You should start to worry. But in my personal experience with skew, in simulation work that I've done, values at around 1.2 will begin to look pretty non-normal. So again, that's just a rule of thumb. Plus or minus 3 is a good proxy for looking at if something is pretty far from normal. So if we're looking at y1 through y3, we can see that y1 is it's good. Nothing is close to plus or minus 3. Y2 may be an issue because kurtosis is above 3 and skew is about 1.25, so I want to look a little bit deeper into y2. And then this doesn't look too bad, but I'll just want to check just to make sure that we're okay there. So just keep a mental note that we will be looking at y2 and y3 later on. Okay. So now we'll go into our first assumption, which is homoscedasticity. And so the way that I like to check homoscedasticity is with a scatterplot matrix. So I'm going to use the pairs function. And the first thing that goes in here is a tilde. If you have a typical keyboard, that should be toward the top left of the keyboard. It's a little squiggly line. And then the variables that we want to create a scatterplot matrix of. So in here, I will be putting in all of the variables. So x1, x2, and then y1 through y3. So y2, and then y3. And then a comma, and then I want to indicate that my data set is regdata3. And then I'm going to give this scatterplot matrix a title. And then I can go ahead and produce the matrix, or the plot here. All right, so I'll press zoom here, and I'll maximize the window here so that we could take a better look at our scatterplot matrix. So this is a really useful tool. It gives you a scatterplot of each variable plotted against every other variable. And so the way to read this is if I'm looking at x1, the scatterplot with x2 is here because it intersects here. The scatterplot with y1 is here. The scatterplot with y2 is here. And the scatterplot with y3 is here. Now you don't have to look at every single scatterplot here. You just want to look at the ones that will be included as models in your analyses. So as you can see, we have 3 criterion variables, and so I'm not going to put all of those into one model at the same time. So I'm not really interested in how y1 and y2 are plotted against each other, or y1 and y3, or y2 and y3. Most likely I'll just be looking at the relationships between x1 and x2, since these are predictors, and then the respective outcome variables. Okay, so when we're looking at these scatter plots here, what we want to see is we don't want to see the residuals getting bigger or smaller as values for one variable increases. So what does that mean? So the best example would be between x1 and y1. Here we can see that as values of x increases, the values of y tend to get more spread out. And so the errors for y are likely to follow and do the same thing. So as we go from lower values of x1 to higher values of x1, we can see that they're more spread out here for y1, and then a little bit more clustered and tightly focused here for lower values of x1. So here is what we call a megaphone shape, and these are the things that we don't want. We don't want the spread or the dispersion of y to increase or decrease on different levels or different values of x. So we can also see that, let's see, we can also see that here a little bit with, hold on, with y2 and x2, where as we get to higher values of x2, the dispersion of y seems to increase. So it's kind of more tightly clustered here and then more widespread out here. So those are things that we want to look for. And so if we find that, like earlier with x1 and y1, then we should start to think about taking a deeper look at a violation of homoscedasticity. All right. So that's a quick check for homoscedasticity. As long as we don't see anything like a megaphone shape or any changes in the dispersion of y conditional on the values of x1 or whatever predictor that you're looking at, then we could be we can be more confident that we haven't violated that assumption. But in our case, given some of the scatter plots in our scatterplot matrix, there may be some violations to homoscedasticity. All right, so moving on to assumption 4 for independent errors, we have I'm going to produce a scatter plot plotting the predictor against the model implied residuals. So to do that, I first have to fit a model. I'll call that fit1. And I'll be using our LM function to estimate the regression model. So I want to predict y2 from x2. And my data set, again, will be reg data 3. And then after fitting my model, I want to take the residuals and plot them against the predictor. So here, I'll put in the predictor, which I'm interested in x2. And then I'm going to plot those against the residuals. I'm going to give my plot a title. So scatter plot of x2 and model residuals. I'm going to change the y label to residuals. And then the x label to x2. Okay, so we'll fit our model, and then once we fit our model, we can use our residuals and plot those. So that's why here I'm calling fit1, and then remember that the $ indicates that I'm grabbing a variable from this object, which is our regression model, and what I want to grab from our regression model are the residuals. So I'll go ahead and plot x2 against the residuals, and then I'll go ahead and zoom here. So what we're looking for here is if our errors are independent, then this should look random. And there should be no pattern in our residuals when they're plotted against our predictor. So in this case, it looks like there might be a pattern here. And one way to more definitively tell if there's a pattern is to use a low S line. And so to plot, to superimpose a low S line, I'm going to use the lines function. Within that, I'm going to use the low S function. And I want to plot reg data 3, x2 against the residuals. And then I have to specify a smoothing parameter. So the low S line is a non-parametric, it's a non-parametric function. And it just kind of, instead of fitting a straight line like we do with a regression line, it more closely follows how the data are plotted. So I have to specify here a smoothing parameter. So higher values of f will give you a smoother line. If you decrease f to something like 0.5 or 0.2, it will give you a more jagged line. So the line will move more with the data than it will be smooth. So here I'll just go ahead and run just this lines function here with the lowest function within it. And then if I zoom, we can see I have my low S line here. So it is showing us that these points are suggesting that there's a pattern here after we account for x2. So remember, we fit our model, so we're predicting x2, we're predicting y2 from x2, and then given the residuals based on the model, it seems like there's still a pattern, that there's still a pattern here. Even though we've already accounted for x2. And what that indicates is that our errors are not independent. So there is a relationship between our residuals and x2 that go above and beyond us already accounting for x2. Okay. So again, when we're checking for independent errors, what we want to see is that after we run our model, we want to see that the residuals are not related in any way to any of our predictors. If any of the scatter plots of the predictors and the residuals show some kind of pattern or relationship, then that is indicating, that is evidence that our errors are not independent. Okay. And then now we move on to assumption 6, so the normally distributed errors assumption. And so first what I'm going to check is the histogram of the variables that we noted earlier that could be non-normal. And those were y2 and y3. So I'll use the hist function. And then in reg data 3, I want to call y2. I'm going to name the x label y2. And I'm going to change the color to olive drab. The other variable that we were interested in was y3. So I will use the hist function one more time. And then from reg data 3, I want to plot y3. I'm going to title the x-axis y3, and then change the color again to olive drab. So if I go ahead and run this histogram, we can see that it does look to be a little bit positively skewed. But again, this could be normal enough. And we could move to more formal tests to test that assumption, but it looks like it could be pretty normal. And that's for y2. And then if we look at y3, this seems to have a more severe positive skew. So again, after looking at our descriptives and seeing that y2 and y3 may have values of skew and kurtosis that are non-normal, in plotting them we can see that there is a bit of positive skew in them. And then we can go ahead and, since we fit our model of predicting y2 from x2, we can see if there's consistency between our plot of the variables and the plot of the residuals. Because remember, our main focus is looking at if the errors are normally distributed, not the variable itself. So we can go ahead and plot our residuals from our model, which is fit1. I'm going to give this a title. I'm going to rename the X label. Now the reason why I'm renaming the X label is because it will print fit1 $sign residuals. It will print as the X label whatever you put in here. And so I don't want that. I just want it to be the variable name, or in this case, residuals. And then again, I'll change the color. And then if I go ahead and run this, we can see that our residuals do look a bit positively skewed. But just as we saw for the histogram of y2, the variable itself, it did look normal-ish. So this could be normal enough to where we don't have to worry about it. And in my personal experience in simulating non-normal data and estimating regression models, the regression model is pretty robust to violations of non-normality. So even with really non-normal variables, the regression seems to be pretty robust to it, and it doesn't seem to affect the estimates or the standard errors. So this might be passable, and we might be able to just run our regression analysis anyway without worrying about this bit of positive skew here. Okay, so again, what we did here was we did some quick checks, visually inspecting some different plots and graphs to check assumption 3, which is homoscedasticity, assumption 4, independent errors, and assumption 6, normally distributed errors. And while the majority of everything looks okay, and it indicates that we can run our regression without worry that our assumptions are too badly violated, there are a couple variables that we may need to take a deeper look at and make sure that the violations of the assumptions aren't too bad. So for example, y2 and y3 seem to be positively skewed, so we may want to run some more formal tests of normality to see if the skew or the kurtosis is really is likely to affect the outcome of our analyses. Another thing is that when we were looking at the scatterplot matrix between y1 and x1, there seemed to be evidence of a violation to homoscedasticity. So we would want to look and maybe run more formal tests on that to see if that violation is likely to affect the analysis or the outcome of our statistical tests. Okay, and so again, this is just a quick check, seeing if we have more work to do and if we should take a deeper look at some of these assumptions. And then we will look at more formal tests of assumption violations when we get into the videos on regression diagnostics. So with that concludes our video on checking regression assumptions in R.